Welcome to this explainer. Today, we're diving into an absolutely exhilarating data science experiment. Seriously, we're looking at a computational framework that dares to completely throw out standard gravitational constants and instead attempts to map the real physical universe using pure wave mechanics. It's basically a massive computational stress test of our cosmos, and wow, the results are absolutely fascinating. So think about this. What if gravity isn't actually what holds the universe together? I mean, standard astrophysics relies super heavily on invisible forces, right? We use concepts like dark matter to explain why galaxies don't just fly apart as they spin. But this radical new computational framework asks a totally different question. It asks, what if space is actually structured by geometric wave resonance? Like, what if the universe isn't being pulled around by invisible mass, but is naturally organizing itself through overlapping standing waves? Okay, here's our roadmap for how we're going to unpack this. We'll start with number 1, the gravity problem. Then 2, a pure wave hypothesis. 3, the 60-phase space. Then we'll run 3 trials. Trial 1 at the galactic scale, Trial 2 in the cosmic web, and finally, Trial 3, diving all the way down to the quantum scale. Let's get into it. Section 1. The gravity problem. Standard astrophysics. Okay, so in the standard model, mass warps spacetime, but here's the catch. When we look at the flat rotation curves of real galaxies, there literally isn't enough visible mass to keep them together, so we've had to rely on invisible dark matter halos just to make the math work out. Well, the wave resonance model takes a completely different path. Instead of forcing a dark matter profile to keep those galaxies from flying apart, the researchers decided to treat the universe like a non-Newtonian fluid. If you've ever played with Oobleck, it's kind of like that. The idea is that high-frequency overlapping vibrations naturally rigidify the medium, creating these structural boundaries completely on their own.
Moving on to Section 2, a pure wave hypothesis, stripping mass dynamics.
What is truly paradigm-shifting about this approach is how it completely alters our perspective. Instead of viewing celestial objects as being actively pulled around by the gravity of some larger mass, this model suggests that spatial coordinates are simply aligning along the stable intersections of overlapping trigonometric fields. So, a planet isn't falling into a gravity well. Rather, the planet is just comfortably tracking a high-pressure node within a standing wave field. To test if this actually works in reality, the team built a highly automated Python engine. And this engine executed 4 exact steps over and over again. First, it ingested millions of raw, unsimulated coordinates. Second, it derived pure, unguided kinetic velocity vectors without hard-coding any speed limits. Third, it applied multi-scale Gaussian filters, which is essentially like blurring the data to find the absolute most stable paths. And fourth, it isolated the scale invariant structural anchors, basically uncovering the core skeleton of the data. They really just wanted to see if raw, unguided kinetic geometry could successfully find structural stability entirely on its own. Which brings us to Section 3, the 60-phase space, streamlined architecture. Now, initially, the engine was bloated with 18 mathematical dimensions, which was slowing down queries and causing a bunch of server timeouts. So by dropping a dozen columns of multi-scale mathematical fluff, they refined their matrix down to a strictly 60-phase space. That means strictly 6 variables per node, 3 for physical spatial position, so x, y, and z, and 3 for movement velocity, vx, vy, and vz. Stripping it down like this allowed the engine to process 60 million pure physical variables simultaneously, directly inside local RAM without freezing up, a real game changer for processing speed. Section 4, Trial 1, Galactic Scale, Mapping the Milky Way. For their first major test, the team connected a live data pipeline directly to the ESA Gaia L2 database. And they mapped out a staggering bounding box. We're talking about a perfect 30 kiloparsec cube, which spans nearly 32,600 light-years across our actual galactic disk and stellar halo. That is a massive chunk of space. And the results of this query? Absolutely wild. By analyzing roughly 10 million real, unsimulated stars inside that cube, the algorithm natively uncovered a striking pressure boundary layer. It maps this forward hemisphere squeeze zone and a trailing tail. But the most amazing part? It did all of this strictly through kinematic network interactions. They didn't insert a single line of generative math or simulated dark matter to make it happen. From this sweeping data run, the math cleanly isolated exactly 10,000 structural anchors from the 100,000 active stellar vectors sampled in the multi-scale macro run. The engine effortlessly smoothed over individual stellar friction and uncovered these massive, large-scale gradient paths. This right here proved that the galaxy maintains geometric structural stability completely on its own, natively, without needing a dark matter halo inserted to hold the math together.
Section 5. Trial 2. Cosmic Web. Observable cosmos.
Scaling things way up, we leave the Milky Way completely behind. At this incredible scale, the 60 tracers are no longer individual stars. They are entire galaxies drifting along the massive intergalactic filaments of the cosmic web. For this one, the team targeted a 30 megaparsec cube using live telemetry from the Sloan Digital Sky Survey. Now, the database server actually choked on the initial request size, but the team used a local coordinate cache bypass to get around it. By hard blocking the coordinates strictly within their 30 megaparsec voxel block, the processor executed the mathematical slice instantly. We're talking about natively processing over 3.5 million real spectroscopic galaxy coordinates in literally a fraction of a second inside the system's RAM. What's completely fascinating about this cosmic trial is the absolute unbroken consistency. The engine mapped a maximum cosmic bound of 25.81 megaparsecs, which is roughly 84 million light-years across. And you know what? The exact same 6D mathematical logic that perfectly organized our local galactic neighborhood also perfectly organized the vast supercluster distribution of the deep universe. Again, doing so without needing any dark energy or dark matter webs to hold those filaments together.
Section 6. Trial 3. Quantum Scale. The Final Frontier.
For the final test, they shrank the bounding box all the way down from megaparsecs to femtometers. By ingesting raw particle accelerator metrics into the exact same 6 columns of math, the system evaluated localized wave packets acting as discrete tracking nodes within a continuous quantum potential field. We're going from the largest structures in the universe down to fundamental subatomic particles. And the computational efficiency here was just astounding. The engine instantly mapped nearly 10 million raw, high-energy particle collision records within a microscopic 30 femtosecond spatial target window. It saved nearly 60 million unguided physical coordinates directly to their local drive, entirely bypassing any network bottlenecks. So, when we build this all into one unified picture, this matrix definitively proves something incredible. Across 3 radically different physical bounds, from a 30 kiloparsec galactic cube to a 30 megaparsec cosmic web, all the way down to a 30 femtometer subatomic space, the exact same stripped-down 60-phase space matrix naturally isolates structural geometry. The identical scale-space filters worked flawlessly across the board, no tweaking required. The researchers noted something really profound here. When their unforced wave field creates a continuous radial gradient, it forms a flawless mathematical mirror of a classical gravitational potential field. So whether you want to label the math mass-derived gravity or phase-locked wave resonance, the geometric skeleton of a collapsing 3D field behaves identical under both theories. The stability lines just emerge naturally from the geometric gradient itself. Okay, so what should you actually take away from this explainer? Well, this massive computational experiment demonstrates that gravity variables are not strictly required to mathematically map the structure of our cosmos. Space can effectively be modeled as a continuous, vibrating fluid system that organizes itself naturally through pure wave intersections. And incredibly, that exact same 6D framework unified the quantum, galactic, and cosmic domains without changing a single underlying rule. Which really leads to a staggering realization. If the exact same 6 spatial and kinetic variables can cleanly organize reality from the tiniest subatomic particles all the way out to the largest superclusters in the cosmic web, without forcing a single gravitational mass constant, well, it leaves us to wonder, is the messiness and chaos of our universe just an illusion, masking a perfectly resonant, interconnected geometric symphony? It absolutely makes you rethink the very fabric of the space around us. Thanks for joining me on this deep dive.